Hello everyone, I am Sakshi from MSc Chemistry first year. Today I am going to read class 11th chemistry book chapter Organic Chemistry, some basic principles and techniques. In the previous unit we have learned the element carbon has a unique property called catenation, due to which it forms covalent bond with other atoms. It also forms covalent bond with atoms of other elements like hydrogen, oxygen, nitrogen, sulfur, phosphorus and halogen. The resulting compounds are studied under a separate branch of chemistry called organic chemistry. This unit incorporates some basic principles and techniques of analysis required for understanding the formation and properties of organic compound. General introduction. Organic compounds are vital for sustaining life on earth and include complex molecules like genetic information bearing deoxyribonucleic acid and protein that constitute essential compound of our blood, muscles and skins. Organic compounds appear in material like clothing, fuels, polymers, dyes and medicines. There are some of the important area of application of these compounds. Science of organic chemistry is about 200-year old. Around the year 1780, chemists began to distinguish between organic compound obtained from the plants and animals and inorganic compound prepared from mineral sources. Berzelius, a Swedish chemist, proposed that a vital force was responsible for the formation of organic compound. However, this notion was rejected in 1828 when F. Holler synthesized an organic compound urea from an inorganic compound ammonium cyanate NH4CNO. Ammonium cyanate transfer heat NH2CONS2 urea. The bonding synthesis of acetic acid by Coles 1845 and that of methane by Berthold 1856 showed consequently that organic compound could be synthesized from inorganic source in a laboratory. The development of electronic theory of covalent bonding used organic chemistry into modern shape. Tetravalence of carbon. Shapes of organic compound. The shape of carbon compound. The knowledge of fundamental concept of molecular structure help in understanding and predicting the properties of organic compound. You have already learned theories of valency and molecular structure in unit 4. Also, you already know the tetravalence of carbon and the formation of covalent bond by it are explained in terms of electronic configuration and hybridization of S and p orbital. It may be recalled that formation and the shape of molecule like methane, CH4, ethene, C2H4, ethine, C2H2 are explained in terms of the use of sp3, sp2 and sp hybrid orbital by carbon atom in the respective molecules. Hybridization influences the bond length and bond enthalpy in compound. The sp hybrid orbital contain more s character and hence it is closer to its nucleus and forms shorter and stronger bond than sp3 hybrid orbital. The sp2 hybrid orbital is intermediate in s character between sp and sp3 and hence the length and enthalpy of the bond it forms are also intermediate between them. The change in hybridization affects the electronegativity of carbon. The greater the s character of the hybrid orbital, the greater is the electronegativity. Thus, a carbon atom having an sp hybrid orbital with 50 s character is more electronegative than that possessing sp2 or sp3 hybridized orbital. This relative electronegativity is reflected in several physical and chemical properties of the molecule concerned, about which you will learn in later units. Some characteristic feature of pi bond. In a pi bond formation, parallel orientation of 2p orbital and adjacent atom is necessary for a proper sideway overlap. Thus, in H2C double bond CH2 molecule, all the atom must be in same plane. The p orbital are mutually parallel and both the p orbital are perpendicular to the plane of the molecule. Rotation of one CH2 fragment with respect to other interference with maximum overlap of p orbital, and therefore such rotation about carbon-carbon double bond is restricted. The electron charge cloud of pi bond is located above and below the plane of the bonding atom. This results in the electron being easily available to the attacking reagent. In general, pi bond provide the most reactive center in the molecule containing multiple bonds. Structural representation of organic compound. Complete contents and bond line structural formula. Structure of organic compound are represented in several ways. The Lewis structure, or dot structure, dash structure, condensed structure, and bond line structure formula are some of the specific types. The Lewis structure, however, can be simplified by representing the two electron covalent dash by a dash structure. Such a structural formula focus on the electron involved in a bond formation. A single dash representing a single bond, double dash is used for double bond, and triple dash represent triple bond. Lone pair of electron on heteroatom, example oxygen, nitrogen, sulfur, halogen, etc., may or may not be shown. Thus ethane C2H6, ethene C2H4, ethine C2H2, and methanol CH3OH can be represented by the following structural formula. Such structural representation are called complete condensed formula. Here are the structural formulas of ethane, ethene, ethine, and methanol. This structural formula can be further abbreviated by omitting some of or all the dash representing covalent bond, and by indicating the number of identical group attached to an atom by a subscript. The resulting expression of the compound is called a condensed structural formula. Thus ethane, ethene, ethine, and methanol can be written as CH3, CH3 ethane, S2C double bond CH2 ethene, SC triple bond CH ethine, CH3OH methanol. Similarly, CH3, CH2, 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 CH3 can be further condensed to CH3, CH2, 6CH3. For further simplification, organic chemists use another way of representing the structure in which only lines are used. In bond line structural representation of organic compound, carbon and hydrogen atoms are not shown, and the line representing carbon-carbon bond are drawn in zigzag fashion. The only atom specifically written are oxygen, chlorine, nitrogen, etc. The terminal denote methyl CH3 group unless indicate otherwise by a functional group, while the line junction denote carbon atom bond. The bond to appropriate number of hydrogen required to satisfy the valency of carbon atom. Some of the examples are represented as follows. In cyclic compound, the bond line formula may be given as cyclopropane, cyclopentane, cyclohexane. Three-dimensional representation of organic molecules. The three-dimensional 3D structure of organic molecule can be represented on paper by using certain convention. For example, by using solid and dash wedge formula. The 3D image of the molecule from two-dimensional picture can be perceived in this formula. The solid wedge is used to indicate a bond projecting out of plane of paper towards the observer. The dash wedge is used to depict the bond projecting out of the plane of the paper and away from the observer. Wedges are shown in such a way that the broad end of the wedge is towards the observer. The bond lying in the plane of the paper are depicted by using a normal line. 3D representation of methane molecule on the paper has been shown. Molecular models. Molecular models are physical devices that are used for a better visualization and perception of three-dimensional shape of organic molecule. They are made up of wood, plastic, and metal and are commercially available. Commonly, three types of molecular models are used: framework model, second, ball and stick model, third, space filling model. In the framework model, only the bond connecting the atom of the molecule and not the atom themselves are shown. This model emphasizes the pattern of bond of molecule while ignoring the size of atom. In the ball and stick model, both the atom and the bond are shown. Balls represent atom and the stick denote a bond. Compound containing C double bond C can best represented by using spring in place of stick. These models are referred to as ball and spring model. The space filling model emphasizes the relative size of each atom based on its van der Waals radius. Bonds are not shown in this model. It conveys the volume occupied by each atom in the molecule. In addition to these models, computer graphite can also be used for molecular modeling. Classification of organic compound. The existing large number of organic compounds and their relative increasing number has made it necessary to classify them on the basis of their structure. Organic compounds are broadly classified as organic compounds divided into two parts: alicyclic or open chain compound, Second is cyclic or closed chain or ring compound. Now cyclic or closed chain or ring compound are divided into two parts, alicyclic compound and aromatic compound. Now alicyclic compound is divided into two parts, homocyclic or carbocyclic compound and heterocyclic compound, non-aromatic. Aromatic compound is divided into three parts, benzenoid compound, non-benzenoid compound and heterocyclic aromatic compound. Acyclic or open chain compound. These compounds are also called as aliphatic compound and contain of straight or branch chain compound. For example, ethane, isobutane, acetaldehyde, acetic acid. Cyclic or closed chain or ring compound. Alicyclic compound. Alicyclic aliphatic cyclic compound contain carbon atom joined in the form of a ring. Cyclopropane, cyclohexene. Sometimes atoms other than carbon are also present in ring. Tetrahydrofuran give below in the example of this type of compound. These exhibit some of properties similar to those of aliphatic compound. Aromatic compound are special type of compound. You will learn about these compound in detail in unit 9. These include benzene and other relative rings compound. Like alicyclic compound, aromatic compound may also have heteroatom in the ring. Such compound are called heterocyclic aromatic compound. Some of the example of various type of aromatic compound are benzenoid aromatic compound, benzene, aniline, naphthalene. Non-benzenoid compound, tropopone. Heterocyclic aromatic compound, furan, thiophene, pyridine. Organic compound can also classified on the basis of functional groups into families or homologous series. Functional groups. The functional group is an atom or group of atoms joined to carbon chain which is responsible for the characteristic chemical properties of the organic compound. The example are hydroxyl group, aldehyde group and carboxylic acid group. Homologous series, a group or series of organic compound each containing a characteristic functional group from a homologous series, and the member of the series are called homologous. The members of homologous series can be represented by general molecular formula, and the successive members differ from each other in a molecular formula by ACS2 unit. There are a number of homologous series of organic compound. Some of these are alkane, alkenes, alkyne, haloalkane, alkanols, alkanones, alkonoic acid, amines, etc. It is also possible that a compound containing two or more identical or different functional groups. This gives rise to polyfunctional compound. Nomenclature of organic compound. Organic compound deal with millions of compounds. In order to clearly identify them, a systematic method of naming has been developed and is known as the IUPAC, International Union of Pure and Applied Chemistry System of Nomenclature. In this systematic nomenclature, the names are correlated with the structure such that the reader or listener can deduce the structure from the name. Before the IUPAC system of nomenclature, however, organic compounds were assigned names based on their organic or certain properties. For instance, citric acid is named so because it is found in citrus fruit, and acid found in red ant is named formic acid, since the Latin word for ant is formica. These names are traditional and are considered as trivial and common names. Some common names are following even today. For example, Buckminster fulgens is a common name given to newly discovered C60 cluster. Nothing is structurally similar to the geodesic domes popularly by the famous architect R. Buckminster Fuller. Common names are useful and in many cases indispensable, particularly when the alternative systematic names are lengthy and complicated. Common names. The IUPAC system of nomenclature. Systematic name of an organic compound is generally derived by identifying the parent hydrocarbon and the functional group attached to it. See the example given below. By further using prefix and suffix, the parent name can be modified to obtain the actual name. Compound containing carbon and hydrogen only are called hydrocarbon. A hydrocarbon is termed saturated if it contains only carbon-carbon single bond. The IUPAC name for homologous series of such compound is alkane. Paraffin was the earlier name given to this compound. Unsaturated hydrocarbons are those which contain at least one carbon-carbon double or triple bond. The IUPAC system of the alkane straight chain hybrid hydrocarbon. The name of such compound are based on their chain structure and end with suffix ane and carry a prefix indicating the number of carbon atoms present in the chain, except from CH4 to C4S10, where the prefix are derived from trivial name. The IUPAC name of some straight chain saturated hydrocarbon are given in table 8.2. The alkane in table 8.2 differ from each other by merely the number of CH2 compound in the chain. They are homologous of alkane series. Branch chain hydrocarbon. In a branch chain compound, small chains of carbon atom are attached at one or more carbon atom of the parent chain. The small carbon chain are called alkyl group. Here is the example. In order to name such compound, the name of alkyl group are prefixed to the name of parent alkane. An alkyl group is derived from a saturated hydrocarbon by removing a hydrogen atom from carbon. Thus CH4A becomes CH3 and is called methyl group, and alkyl group is named by substituting YL for N in the corresponding alkane. Abbreviations are used for some alkyl groups. For example, methyl is abbreviated as Me, ethyl as ET, propyl as PR, and butyl as BU. The alkyl groups can be branched also. Thus, propyl and butyl groups can have branch structure as formula. Common branch group have specific trivial names. For example, the propyl group can either be N-propyl group or isopropyl group. The branch butyl group are called sec-butyl, isobutyl, and tert-butyl group. We can also encounter the structural unit CH2CCS33, which is called neopentyl group. Nomenclature of branch chain alkanes. We encounter a number of branch chain alkane. The rules for naming them are given below. First of all, longest chain carbon in molecule is identified. In the example given below, the longest chain has 9 carbon and it is considered as the parent or root chain. Selection of parent chain as shown in second is not correct because it has only 8 carbons. The carbon atom of parent chain is numbered to identify the parent alkane and to locate the position of the carbon atom. H with branching take place due to the substitution of alkyl group in place of hydrogen atom. The numbering is done in such a way that the branch carbon atom get the lowest possible number. Thus, the numbering in the above example should be from left to right and not from right to left. The name of the alkyl group attached as a branch are then prefixed to the name of parent alkane, and position of substituent is indicated by appropriate number. If different alkyl groups are present, they are listed in alphabetic order. Thus, name for the compound shown above is 6-ethyl 2-methylnonane. The numbers are separated from the group by hyphens and there is no break between methyl and nonane. If two or more identical substituent group are present, then the number are separated by commas. The name of identical substituent are not repeated. Instead, prefix such as a di for 2, tri for 3, tetra for 4, penta for 5, hexa for 6, etc. are used while writing the name of the substituent in alphabetic order. These prefixes, however, not considered. Thus, the following compounds are named as: if the two substituents are found in equivalent position, the lower number is given to the one coming first in the alphabetical listing. Thus, the following compound is 3-ethyl 6-methyloctane and not 6-ethyl 3-methyloctane. The branch alkyl group can be named as following the above mentioned procedure. However, the carbon atom of branch that attaches to the root alkane is number 1 as amplified below. The name of such branched chain alkyl group is placed in parentheses while naming the compound. While writing the trivial name of substituent in alphabetical order, the prefix iso and neo are considered to be the part of fundamental name of alkyl group. The prefix sect and tert are not considered to be the part of fundamental name. The use of iso and related common prefix for naming alkyl group is also allowed by the IUPAC nomenclature as long as these are not further substituted in substituted compound. The following rules may be also remembered. If there happen to be two chains of equal size, then that chain is to be selected which contain more number of side chain. After selection of chain numbering, it is to be done from end closer to the substituent. Cyclic compound. A saturated monocyclic compound is named by prefix cyclo to the corresponding straight chain alkene. If side chains are present, then the rules given above are applied. Name of some cyclic compounds are given below. Cyclopentane 1-methyl 3-propyl cyclohexane 3-ethyl 1,1-dimethyl cyclohexane. Nomenclature of organic compound having functional groups. A functional group, as defined earlier, is an atom or group of atoms bonded together in a unique manner, which is usually the site of chemical reactivity in an organic molecule. Compound having the same functional group undergo similar reaction. For example, CH3OH, CH3CH2OH, and CH3 twice CHOH, all having OH functional group, liberate hydrogen on reaction with sodium metal. The presence of functional group enable systematization of organic compound into different classes. For example of some functional group with their prefix and suffix, also with some of example of organic compound possessing. First of all, the functional group present in the molecule is identified with the determination, the choice of appropriate suffix. The longest chain of carbon atom containing the functional group is numbered in such a way that the functional group is attached at the carbon atom possessing lowest possible number in the chain. By using the suffix, the name of compound is arrived at. In the case of polyfunctional compound, one of the functional group is chosen as the principal functional group and the compound is then named on that basis. The remaining functional group, which are subordinate functional group, are named as substituent using the appropriate prefix. The choice of principal functional group is made on the basis of order of preference. The order of decreasing priority for some functional group is COOH, SO3H, COOR, COCl, CONH2, CN, HC double bond O, C double bond OH, OH, NH2, C double bond C, C triple bond C. The R, C6H5 halogens, NO2, alloxy, etc. are always prefix substituent. Thus a compound containing both an alcohol and a keto group is named as hydroxyalconane, since the keto group is preferred to the hydroxyl group. For example, HOCH2, CH2 thrice, CH2CO, CH3 will be named as a 7-hydroxyheptane 2 on and not 2 oxoheptane 7-ol. Similarly, Br2CH, double bond CH2 is named as 3-bromoprop 1-ene, not 1-bromoprop 2-ene. If more than one functional group of the same type are present, their number is indicated by adding di, tri, etc. before the class suffix. In such cases, the full name of the parent alkane is written before the class suffix. For example, CH2OH is named as ethane 1,2-diol. However, the ending Ne of the parent alkane is dropped in the case of compound having more than one double or triple bond. For example, CH2 double bond CH double bond CH2 is named as buta 1,3-diene. Nomenclature of substituent benzene compound. For IUPAC nomenclature of substituent benzene compound, the substituent is placed at prefix to the word benzene as shown in the following example. However, common names of many substituent benzene compounds are also universally used. Methylbenzene, toluene, methyl oxybenzene, anisole, aminobenzene, aniline, nitrobenzene, bromobenzene. If benzene ring is distributed by the position of substituent is defined by numbering the carbon atom of the ring such that the substituent located at the lower number possible. For example, the compound is named as 1,3-dibromobenzene and not as 1,5-dibromobenzene. In the trivial system of the nomenclature, the terms ortho, meta, and para are used as prefix to indicate the relative position 1, 2, 1, 3, and 1, 4 respectively. Thus, 1,3-dibromobenzene is named as a dibromobenzene. Meta is abbreviated as M, and the other isomer of dibromobenzene 1,2-A and 1,4-C are named as ortho and para dibromobenzene respectively. For tri and highest substituted benzene derivative, these prefixes cannot be used, and the compound are named by the identifying substituent position on the ring by following the lowest locant rule. In some cases, common names of benzene derivatives taken as base compound. Substituent of the base compound is assigned number 1, and then direction of numbering is chosen such that the next substituent gets the lowest. The substituent appear in the name is the alphabetical order. Here are some example: 1-chloro-2,4-dinitrobenzene, 2-chloro-1-methyl-4-nitrobenzene, 2-chloro-4-methyl-anisole, 4-ethyl-2-methyl-aniline, 3,4-dimethyl phenol. When a benzene ring is attached to the alkane with a functional group, it is considered as substituent instead of a parent. The name for benzene as substituent is phenyl C6H5, also abbreviated as PH. Isomerism: the phenomenon of existence of two or more compounds possessing the same molecular formula but different properties is known as isomerism. Such compounds are also called isomers. The following flowchart show different types of isomerism. Structural formula: structural isomerism: compounds having the same molecular formula but different structural are called as structural isomerism. Some typical examples of different types of structural isomerism are given below. Chain isomerism: isomer is divided into two parts: structural isomerism and stereoisomerism. Structural isomerism is divided into four parts: chain isomerism, position isomerism, functional group isomerism, and metamerism. Stereoisomerism divided into two parts: geometrical isomerism and optical isomerism. Chain isomerism: when two or more compounds having similar molecular formula but different carbon skeleton. These are referred to as chain isomerism, and the phenomena is termed as chain isomerism. For example, C5H12 represents three compounds: CH3, CH2, 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 CH3. Pentane, isopentane, neopentane. Position isomerism: when two or more compounds differ in the position of substituent atom or functional group on the chain skeleton, they are called position isomerism, and this phenomenon is termed as position isomerism. For example, the molecular formula C3H8O represents 2 alcohol, propane 1 ol, propane 2 ol. Functional group isomerism: two or more compounds having the same molecular formula but different functional group are called functional isomerism, and this phenomenon is termed as functional group isomerism. For example, the molecular formula C3H6O represents an aldehyde and a ketone, propanone and propanol. Metamerism: it arises due to the different alkyl chains or either side of functional group in the molecule. For example, C4H10O represents methoxypropane, CH3O, C3H7 and ethoxyethane, C2H5O, C2H5. Stereoisomerism: the compound that have the same constituent and sequence of covalent bond but differ in relative position of their atom or group in space are called stereoisomerism. This special type of isomerism is called stereoisomerism and can and can be classified as geometrical and optical isomerism. Fundamental concept in organic reaction mechanism. In an organic reaction, the organic molecules react with an appropriate attacking reagent and lead to the formation of one or more intermediate and finally product. The general reaction is depicted as organic molecule, substrate, attacking reagent, intermediate, byproduct, and product. Separate is that reactant which supplies carbon to the new bond, and the other reactant is called reagent. If both the reactants supply carbon to new bond, then choice is arbitrary, and in that case the molecule on which attention is focused is called substrate. In such a reaction is a covalent bond between two carbon atom or a carbon and some other carbon is broken and a new bond is formed. A subsequential account of each step describing detail of each movement, energetic during bond cleavage and bond formation, and the rate of transformation of reactant into product is referred as a reaction mechanism. The knowledge of reaction mechanism help in understanding the reactivity of organic compound and in planning strategy of their synthesis. In the following section, we have learned some of the principles that explain how this reaction takes place. Fission of covalent bond. A covalent bond can get cleaved either by hydrolytic cleavage or by homolytic cleavage. In hydrolytic cleavage, the bond break in such a fashion that the shared pair of electrons remain with one of the fragment. After hydrolysis, one atom has a sextet electronic structure and a positive charge, and the other a valence octet with at least one lone pair and a negative charge. Thus, electrolytic cleavage of bromomethane will give CS3 positive and Br negative as shown. A species having a carbon atom possessing sextet of electron and a positive charge is called a carbocation. The C positive S3 ion is known as methyl cation or methyl carbonium ion. Carbocation are classified as primary, secondary, and tertiary depending on whether 1, 2, or 3 carbon are directly attached to the positively charged carbon. Some other examples of carbocations are CH3, C positive, S2 ethyl cation, a primary carbocation, CH3 twice C positive isopropyl cation, a secondary carbocation, and CH3 thrice C positive tert butyl cation, a tertiary carbocation. Carbocation are highly unstable and reactive species. Alkyl group directly attached to the positively charged carbon stabilize the carbocation due to inductive and hyperconjugation effect, which you will be study in section 8.7.5 and 8.7.9. The observed order of carbocation stability is C positive CH3, C positive S2, CH3 twice C positive CH3 thrice C positive. These carbocation having trigonal planar shape with positively charged carbon being sp2 hybridized. Thus, the shape of C positive S3 may be considered as being derived from the overlap of C equivalent CsP2 hybridized orbital with one s orbital of each of 3 hydrogen atom. Each bond may be represented as CsP2 H sigma bond. The remaining carbon atom is perpendicular to the molecular plane and contain no electron. The heterolytic cleavage can also give a species in which carbon atom the shared pair of electron. For example, when Z attached to the carbon leaves without electron pair, the methyl anion is formed. Such a carbon species carrying a negative charge on charged atom is called carbanion. Such carbon is generally sp3 hybridized and its structure is distorted tetrahedron. Carbanion are also unstable and reactive species. The organic reaction which proceed through hydrolytic bond cleavage are called ionic and heteropolar or just polar reaction. In homolytic cleavage, one of the electron of shared pair in a covalent bond goes with each of the bonded atom. Thus, in a homolytic cleavage, the movement of the single electron takes place instead of an electron pair. The single electron movement is shown by half-headed curved arrow. Such cleavage result in the formation of neutral species which contain an unpaired electron. These species are called free radical. Like carbocation and carbanion, free radicals are also very reactive. A homolytic cleavage can be shown as aryl. Alkyl radicals are classified as primary, secondary, and tertiary. Alkyl radical stability increases as we proceed from primary to tertiary. Organic reactions which proceed by homolytic fusion are called free radical or homopolar or non-polar reactions. Substrate and reagent ions are generally not formed in the reaction of organic compound molecules as such participate in the reaction. It is convenient to name one reagent as substrate and other as reagent. In general, a molecule whose carbon is involved in new bond formation is called substrate and the other one is called reagent. When carbon-carbon bond is formed, the choice of remaining the reagent as substrate and reagent is arbitrary and depend on molecule under observation. Nucleophile and electrophile reagent attack the reactive site of the substrate. The reactive site may be electron deficient portion of the molecule. Example, an atom with incomplete electron shell or positive end of the dipole in the molecule. If the attacking species is electron rich, it attacks these sites. If attacking species is electron deficient, the reactive site for it is that part of substrate molecule which can supply pi electron in a double bond. The reagent that bring an electron pair to the reactive site is called a nucleophile. Nucleophile seeking and nucleus seeking and then reaction is then a nucleophilic. A reagent that take away an electron pair from a reactive site is called electrophile. Electron seeking and the reaction is called electrophile. During a polar organic reaction, a nucleophile attack an electrophile center of the substrate, which is that specific atom of or part of substrate which is electron deficient. Similarly, an electrophile attack at a nucleophile center which is the electron rich center of the substrate. Thus, the electrophile receive electron pair from the substrate when the two undergo bonding interaction. A curved arrow notation is used to show the movement of an electron pair from the nucleophile to the electrophile. Some examples of nucleophile are the negatively charged ion with the lone pair of electron, such as hydroxide, dicyanide ions, and carbanion. Neutral molecules as H2O, R3N, R2NH, etc. can also act as nucleophile due to the presence of lone pair of the electron. Example of electrophile include cation and neutral molecules having functional group like carbonyl group or alkyl halides. The carbon atom in carbocation has sextet configuration, hence it is electron deficient and can receive a part of electron from the nucleophile. In neutral molecules such as alkyl halide, due to polarity of CX bond, a partial positive charge is generated on the carbon atom and hence the carbon atom becomes an electrophile center at which a nucleophile can attack. Electron movement in organic reaction. The movement of electron in organic reaction can be shown by curved arrow notation. It shows how change in bonding occur due to electron redistribution during the reaction. To show the change in position of pair of electron, curved arrow start from the point from where an electron pair is shifted and at the location to which the pair of electron may move. Presentation of shifting of electron pair is given below. Movement of single electron is indicated by a single barbed fish hook. For example, in transfer of hydroxide ion giving ethanol and in the dissociation of chromomethane, the movement of electron using curved arrow can be depicted as follows. Electron displacement effect in covalent bond. The electron displacement in an organic molecule may take place either in the ground state under the influence of an atom or a substituent group or in the presence of an appropriate attacking reagent. The electron displacement due to the influence of an atom or a substituent group present in the molecule cause permanent polarization of the bond. Inductive effect and the resonance effect are example of this type of electron displacement. Temporary electron displacement effect are seen in the molecule when a reagent approaches to attack it. This type of electron displacement is called electromeric effect or polarizability effect. In the following section, we will learn about this type of electronic displacement. Inductive effect: when a covalent bond is formed between atoms of different electronegativity, the electron density is more toward the more electronegative atom of the bond. Such a shift of electron density results in a polar covalent bond polarity leads to various electron effects in organic compounds. Let us consider chloroethane, in which the CCl bond is polar covalent bond. It is polarized in such a way that the carbon 1 gain the same positive charge and chlorine some negative charge. The fractional electronic charge on the two atoms in a polar covalent bond are denoted by symbol delta, and shift of electron density is shown by an arrow that points from delta positive to delta negative end of the polar bond. In turn, carbon 1, which has developed partial positive charge, draws some electron density toward it from the adjacent CC bond. Consequently, some positive charge develop on carbon 2 also, where symbolizes relatively some smaller positive charge as compared to that on carbon 1. In other words, the polar CCl bond induces polarity in the adjacent bond. Such polarization of a sigma bond caused by the polarization of adjacent sigma bond is referred to as inductive effect. This effect is passed on the subsequent bond also, but the effect decreases rapidly as the number of interweaving bond increases and become vanishing small after free bond. The inductive effect is related to the ability of substituent to either withdraw or donated electron density to attach carbon atom. Based on this ability, the substituent can be classified as electron withdrawing or electron donating group relative to hydrogen, halogen, and many other groups such as nitro, cyano, carboxyl, ester, aryl oxy, etc. are electron withdrawing group. On the other hand, the alkyl group like methyl and ethyl are usually considered as electron donating group. Resonance structure: there are many organic molecules whose behavior cannot be explained by a single Lewis structure. An example is that of benzene. Its cyclic structure containing alternating C single and C double bond shown in inadequate for explaining its characteristic properties. As per the above representation, benzene should exhibit two different bond lengths due to C single and C double bond. However, as determined experimentally, benzene has a uniform CC bond distance of 139. A value intermediate between CC single 154 pm and C double 139 pm bond. Thus, the structure of benzene cannot be represented adequately by the above structure. Further, benzene can be represented equally well by the energetically identical structure 1 and 2. Therefore, according to the resonance theory, the actual structure benzene cannot be adequately represented by any of these structures. Rather, it is a hybrid of the two structures called resonance. The resonance structure, conical structure or contributing structure, can hypothetical and individually do not represent any real molecule. They contribute to the actual structure in portion of their stability. And another example of resonance is provided by nitromethane, which can be represented by two Lewis structure. There are two types of NO bond in this structure. However, it is known that the two NO bond of nitromethane are of the same length, intermediate between a NO single and a N double bond or double bond. The actual structure of nitromethane is therefore a resonance hybrid of two conical forms 1 and 2. The energy of actual structure of the molecules is lower than that of any of the conical structure. The difference in energy between the actual structure and the lowest energy resonance structure is also called resonance stabilization energy, or simply the resonance energy. The more the number of important contribution structure, the more is the resonance energy. Resonance is particularly important when the contributing structure are equivalent in energy. The following rules are applied while writing the resonance structure. The resonance structure have the same position of the nuclei and the same number of unpaired electrons. Among the resonance structure, the one which has more number of covalent bond, all the atom with octet of electron less separation of opposite charge, and more dispersal of charge is more stable than others. Resonance effect. The resonance effect is defined as the polarity produced in the molecule by the interaction of two pi bond or between pi bond and lone pair of electron present or an adjacent atom. The effect is transmitted through the chain. There are two types of resonance or mesomeric effect designated or as P or R or M effect. Positive resonance effect plus R effect. In this effect, the transfer of electron is away from the atom or substituent group attached to the conjugated system. The electron displacement makes certain position in the molecule of high electron density. This effect is aniline is shown as negative resonance effect minus R effect. This effect is observed when the transfer of electron is toward the atom of the substituent group attached to conjugated system. For example, nitrobenzene. This electron displacement can be depicted as the atom or substituent group which represent plus R or minus R. Electron displacement effect are as follow: plus R effect halogen OH, OR, OC, OR, NH2, NHR, NR2, NHCOR. Minus R effect COH, CHO, C double bond O, CN, NO2. The presence of alternate single and double bond in an open chair or cyclic system is termed as conjugate system. These systems often show abnormal behavior. The example are 1,3-butadiene in aniline and nitrobenzene, etc. In such system, the pi electrons are delocalized and the system develops polarity. Electromeric effect. E effect. It is a temporary effect. The organic compound have a multiple bonds. Shown this effect in the presence of an attacking reagent only. It is defined as the complete transfer of shared pair of pi electron to one of the atom joined by a multiple bond on the demand of an attacking reagent. The effect is annulled as shown as the attacking reagent is removed from the domain of the reaction. It is represented by E and the shifting of the electron is shown by curved arrow. There are two distinct types of electromeric effect: positive electromeric effect plus E effect. In this effect, the pi electron of the multiple bond are transferred to the atom to the reagent get attached. Negative electromeric effect minus E effect. In this effect, the pi electron of the multiple bond are transferred to that of the atom to which attacking reagent does not get attached. For example, when inductive and electromeric effect operate in opposite direction, the electromeric effect predominate. Hyperconjugation is a general stabilizing interaction. It involves delocalization of pi electron of CH bond of alkyl group directly attached to an atom of unsaturated system or to an atom with an unshared p orbital. The sigma electron of CH bond of the alkyl group enter into partial conjugation with attached unsaturated system or with the unshared p orbital. Hyperconjugation is a permanent effect. The unsaturated hyperconjugation effect. Let us take an example of CH3C positive S2 in which the positively charged carbon atom has the empty p orbital. One of the CH bond of the methyl group can align in the plane of empty p orbital and the electron constituting the CH bond in the plane with this p orbital can be delocalized in the empty p orbital. As this type of overlap stabilizes the carbocation because electron density from adjacent sigma bond help in disappearing the positive charge. In general, greater the number of alkyl group attached to a positively charged carbon atom, the greater is the hyperconjugation interaction and stabilization of the carbon. Thus, we have the following relative stability of the carbon cation. Hyperconjugation is also possible in alkene and alkyl. Delocalization of electron by hyperconjugation in case of alkene can be depicted as there are various ways of looking at the hyperconjugation effect. On the other way is to regard CH bond as possessing partial ionic character due to resonance. The hyperconjugation may also be regarded as no bond resonance. Type of organic reaction and mechanisms. Organic reaction can be classified into following categories: substituent reaction, addition reaction, elimination reaction, rearrangement reaction. Method of purification of organic compound. Once an organic compound is extracted from a natural source or synthesis in the laboratory, it is essential to purify it. Various methods used for purification of organic compound are based on the nature of compound and the impurity present in the. Common techniques used for purification are as follows: sublimation, crystallization, distillation, differential extraction, and chromatography. Finally, the purity of compound is ascertained by determining the melting or boiling point. Most of the pure compound have sharp melting point and the boiling point. New method of checking the purity of an organic compound are based on different type of chromatographic spectroscopic techniques. Sublimation. You have learned earlier that on heating some solid substances change from solid to vapor state without passing through the liquid state. The purification technique based on the above principle is known as sublimation and used to separate sublimable compound from non-sublimable impurities. Crystallization. This is one of the most commonly used technique for the purification of solid compound. It is based on the difference in the solubilities of the compound and the impurities in a suitable solvent. The impure compound is dissolved in a solvent in which it is sparingly soluble at room temperature but appreciably soluble at higher temperature. The solution is concentrated to get a nearly saturated solution. On cooling, the solution pure compound crystallizes out and is removed by filtration. The filtrate contains impurities and small quantity of the compound. If the compound is highly soluble in one solvent and very little soluble in other solvent, crystallization can be satisfactorily carried out in mixture of these solvent. Impurities which impart color to the solution are removed by absorbing or activated charcoal. Repeated crystallization becomes necessary for purification of compound containing impurities of comparable solubilities. Distillation. This important method is very used to separate volatile liquid from non-volatile impurities, and the liquid having sufficient difference in their boiling point. Liquid having different boiling point vaporizes at different temperature. The vapor are cooled and the liquids are formed are collected separately. Chloroform and aniline are easily separated by the technique of distillation. The liquid mixture is taken in a round bottom flask and heated carefully. On boiling, the vapor of lower boiling component are formed first. The vapor are condensed by using a condenser and liquid is collected in a receiver. The vapor of higher boiling component form later and the liquid can be collected separately. Fractional distillation. If the difference in boiling point of two liquids is not much, simple distillation cannot be used to separate them. The vapor of such liquid are formed within the same temperature range and are condensed simultaneously. The technique of fractional distillation is used in such cases. In this technique, vapor of a liquid mixture are passed through a fractional column before condensation. The fractional column is fitted over the mouth of the round bottom flask. Vapor of a liquid with a higher boiling point condensed before the vapor of the liquid with other boiling point. The vapor rising up in the fractional column become richer in very volatile component. By the time the vapor reaches to the top of the fractional column, these are rich in the more volatile component. Fractionating column are available in various sizes and design. A fractionating column provide many surfaces for heating exchange between the ascending vapor and the descending condensed liquid. Some of the condensed liquid in the fractionating column obtain heat from the ascending vapor and revaporize the vapor, thus become richer in low boiling component. The vapor of low boiling component ascend to the top of the column. On reaching the top, the vapor become pure in low boiling component and pass through the condenser, and the pure liquid is collected in receiver. After a series of successive distillation, the remaining liquid of the distillation flask get enriched in high boiling component. Each successive condensation and vaporization until in the Kneading column is called a theoretical plate. Commercially, columns with hundreds of plates are available. One of the technological application of fractional distillation is to separate different fractional of crude oil in petroleum industry. Distillation under reduced pressure. This method is used to purify liquid having very high boiling point and those which decompose at or below their boiling point. Such liquid are made to boil at a lower temperature lower than their normal boiling point. By reducing the pressure on their surface, a liquid boil at a temperature at which its vapor pressure is liquid to the external pressure. The pressure is reduced with the help of water pump or vacuum pump. Glycerol can be separated from spent oil in a soap industry by using the technique. Steam distillation. The technique is applied to separate substances which are steam volatile and are immiscible with water. In steam distillation, steam from a steam generator is passed through a heated flask containing the liquid to be distilled. The mixture of steam and the volatile organic compound is condensed and collected. The compound is later separated from water using a separating funnel. In steam distillation, the liquid boil when the sum of vapor pressure due to the organic liquid and that due to water become equal to the atmospheric pressure, that is P is equals to P1 plus P2. Since P1 is lower than P, the organic liquid vaporizes at low pressure temperature and then its boiling point. Then thus if one of the substance in the mixture is water and the other a water insoluble substance, then the mixture will boil close to but below 373 Kelvin. A mixture of water and the substance is obtained which can separate by using a separating funnel. Aniline is separated by a technique from aniline water mixture. Differential extraction. When an organic compound is present in aqueous medium, it is separated by shaking it with an organic solvent in which it is more soluble than in water. The organic solvent and the aqueous solution should be immiscible with each other so that they form two distinct layers which can be separated by separatory funnel. The organic solvent is later removed by distillation or by evaporation to get back the compound. Differential extraction is carried in a separatory funnel. In the organic compound is less soluble in the organic solvent. A very large quantity of solvent would be required to extract even a very small quantity of the compound. The technique of continuous extraction is employed in such cases. In the technique, some solvent is repeatedly used for extraction and of the compound. Chromatography. Chromatography is an important technique extensively used to separate mixture into their component, purify compound and also to test the purity of compound. The name chromatography is based on the Greek word chroma for color, since the method was first used to separate of colored substances from found in plants. In this technique, the mixture of substances is applied into a stationary phase which may be solid or liquid. A pure solvent, a mixture of solvent or a gas, is allowed to move slowly over the stationary phase. The component of the mixture get gradually separated from the another. The moving phase is called the mobile phase. Based on the principle involving chromatography is classified in different categories. Two of these are adsorption chromatography and partition chromatography. Adsorption chromatography is based on the fact that different compounds are absorbed on adsorbent to different degrees. Commonly used adsorbent are silica gel and alumina. When a mobile phase is allowed to move over a stationary phase, the component of the mixture move by varying distances over the stationary phase. Following are two main type of chromatography technique on the principle of different adsorption: column chromatography and thin layer chromatography. Column chromatography. Column chromatography involves separation of a mixture over a column of absorbent peaks packed in a glass tube. The column is fitted with a stopcock at its lower end. The mixture absorbed on adsorbent is placed on the top of adsorbent column packed on in a glass tube, and appropriate eluent, which is a liquid or a mixture of liquid, is allowed to flow down in column slowly depending upon the degree to which the compound are absorbed. Complete separation take place. The most readily absorbed substances are retained near the top and other come down to various distances in the column. Thin layer chromatography. The thin layer chromatography is another type of adsorption chromatography which involves separation of substituent, a mixture, or a thin layer of adsorbent cut on the glass plate. A thin layer of an adsorbent is separated over a glass plate of suitable size. The plate is known as thin layer chromatography plate or chroma plate. The solution of the mixture to be separated is applied as a small spot about 2 cm above end of the TLC plate. The glass plate is then placed in a closed jar containing the eluent. As the eluent rises up the plate, the component of mixture move up along the eluent to different distances depending on their degree of adsorption and separation take place. The relative adsorption of each component of the mixture is expressed in terms of a retardation factor, that is R value. Rf is equal to distance moved by the substance from baseline, distance moved by the solvent from the baseline. The spot of colored compound are visible on TLC plate due to their original color. The spot of colorless compound, which are invisible to the eye but fluorescence in ultraviolet light, can be detected by putting the plate under ultraviolet light. Another detection technique is to place the plate in a covered jar containing a few crystals of iodine. Spot of the compound which absorb iodine will show up as brown spot. Sometimes an inappropriate reagent may also be sprayed on the plate. For example, amino acid may be detected by spraying the plate with ninhydrin solution. Partition chromatography. Partition chromatography is based on the continuous differential partition of the component of a mixture between stationary and mobile phases. Paper chromatography is a type of partition chromatography. In paper chromatography, a special quantity of paper known as chromatography paper is used. Chromatography paper contains water trapped in it, which acts as a stationary phase. A strip of chromatography paper spotted at the base with the solution of mixture is suspended in a suitable solvent of mixture of solvent. Thus, this solvent acts as the mobile phase. The solvent raises up the paper by capillary action and flow over the spot. The paper selectively retain different components according to their differing partition in the two phases. The paper strip so developed is known as chromatogram. The spots of the separated color compound are visible at different height from the position of initial spot on the chromatograph. The spot of the separated colorless compound may be observed either under ultraviolet light or by the use of appropriate spray reagent as discussed under thin layer chromatography. Qualitative analysis on organic compound. The elements present in organic compound are carbon and hydrogen. In addition to these, they may also contain oxygen, nitrogen, sulfur, halogen, and phosphorus. Detection of carbon atom and hydrogen. Carbon and hydrogen are detected by heating in the compound with copper to oxide. Carbon present in the compound is oxidized to carbon dioxide and hydrogen to water with detection of other elements. Nitrogen, sulfur, halogen, and phosphorus present in organic compound are detected by Lagrangian test. The elements present in the compound are converted from covalent form into the ionic form by fusion the compound with sodium metal. C and S and X from the organic compound. Cyanide, sulfide, and halides of sodium formed on sodium fusion are extracted from the fused mass by spoiling it with distilled water. The extract is known as sodium fusion extract. Test for nitrogen. The sodium fusion extract is boiled with iron to sulfate and then acidified with concentrated sulfuric acid. The formation of Persian blue color form the presence of nitrogen. Sodium cyanide first react with iron sulfate and form sodium hexacyanopyrite on heating with concentrated sulfur acid. Some iron are oxidized to iron ions which react with sodium hexacyanopyrite to produce iron 3 hexacyanopyrite, which is Persian blue in color. Test for sulfur. The sodium fusion extract is acidified with acetic acid and lead acetate is added to it. Black precipitate of lead sulfide indicate the presence of sulfur on treatment. Sodium fusion extract with sodium nitroprusside appearance of violet color further indicate the presence of sulfur. In case nitrogen and sulfur both are present in the organic compound sodium thiocyanate is formed, it gives blood red color and no Persian blue since there are no free cyanide ions. If sodium fusion is carried out with excess of sodium, the thiocyanate decompose to yield cyanide and sulfide. These ions give their usual test for halogen. The sodium fusion extract is acidified with nitric acid and then treated with silver nitrated white precipitate soluble in ammonium hydroxide solution. The presence of chlorine, a yellowish precipitate springly soluble in ammonium hydroxide shown the presence of bromine and yellow precipitate insoluble in ammonium hydroxide as shown the presence of iodine. If nitrogen or sulfur is also present in the compound, the sodium fusion extract is first boiled with concentrated nitric acid to decompose cyanide or sulfide of sodium formed during legendary test. These ions would otherwise interfere with silver nitrate. Test for the halogen. Test for phosphorus. The compound is heated with sodium agent. The phosphorus present in the compound is oxidized to phosphate. The solution is boiled with nitric acid and then treated with ammonium molybdate. A yellow coloration of or precipitate indicate the presence of phosphorus. Qualitative analysis of compound is very important in organic chemistry to help chemists in the determination of mass percent of element present in the compound. You learnt in unit 1 that mass percent of element is required for the determination empirical and molecular formula. The percentage composition of element present in organic compound determined by the following method. Carbon and hydrogen. Both carbon and hydrogen are estimated in one experiment. A known mass of organic compound is burnt in the presence of excess of oxygen and carbon dioxide. Carbon and hydrogen in the compound are oxidized to carbon oxide and water respectively. The mass of water produced is determined by passing the mixture through a waste U-tube containing anhydrous calcium chloride. Carbon dioxide is present in another U-tube containing concentrated solution of potassium hydroxide. These are connected in series. The increase in masses of calcium chloride and potassium hydroxide give the amount of water and carbon dioxide from which the percentage of carbon and hydrogen are calculated. Let the mass of organic compound, the mg mass of water and carbon dioxide produced be m1 and m2 gram g respectively. Percentage of carbon 12 into mg into 100 by m, 44 into m. Percentage of hydrogen 2 into m1 into 100 by m, 18 into m. Nitrogen. There are two methods of estimation of nitrogen: Dump's method and Cage-Hall method. Dump's method. The nitrogen containing organic compound when heated with copper oxide is an atmosphere of carbon dioxide yield free nitrogen in addition to carbon dioxide and water. Traces of nitrogen oxide formed, if any, are reduced to nitrogen by passing the gaseous mixture over a heated copper gauge. The mixture of gases so produced is collected over an aqueous solution of potassium hydroxide which absorbs carbon dioxide. Nitrogen is collected in the upper part of the graduated tublet. The mass of organic compound is equals to mg. Volume of nitrogen collected is equals to V1 ml. Room temperature T1 K. Volume of nitrogen at STP P1 V1 into 273 by 760 into T1. Let it be VML where P1 and V1 are the pressure and the volume of nitrogen. P1 is different from the atmospheric pressure at which nitrogen gas is collected. The value of P1 is obtained by the relation P1 is equal to atmospheric pressure minus aqueous tension 22400 ml and to STP weight 28 gram. VML and to S at STP weight 28 into V by 22400 gram. Percentage of nitrogen 28 into V into 100 by 22400 m. Kajal-Hall's method. The compound containing nitrogen is heated with the concentrated sulfuric acid. Nitrogen in the compound get converted into ammonium sulfate. The resultant acid mixture is then heated with excess of sodium hydroxide. The liberated ammonia gas is absorbed in the excess of standard solution of sulfuric acid. The amount of ammonia produced is determined by estimating the amount of sulfuric acid consumed in the reaction. It is done by estimating unreacted sulfuric acid left after the absorption of ammonia by titrating it with standard alkali solution. The difference between the initial amount of acid taken and that left after the reaction gives the amount of acid. Reaction with ammonia organic compound plus H2SO4 gives NH4 twice SO4 and 2NaOH Na2SO4 plus 2NH3 plus 2H2O 2NH3 plus H2SO4 gives NH4 twice SO4. Let the mass of organic compound taken is equals to mg. Volume of H2SO4 of molarity m taken is equals to V ml. Volume of NaOH of molarity m is used for titration of excess of H2SO4 is equals to V1 ml. V1 ml of NaOH of molarity m V by 2 ml of H2SO4 of molarity m is volume of H2SO4 of molarity m n used is equals to V minus V1 by 2 ml. V minus V1 by 2 ml of H2SO4 of molarity is equals to V 2 into V minus V1 by 2 ml of NH3 solution of molarity m. 1000 ml of 1 m NH3 solution contains 17 gram NH3 or 14 gram of N 2 into V minus V1 by 2 ml of NH3 solution of molarity m contain 14 into m into 2 into V minus V1 by 2 by 1000 gn. Percentage of N is equals to 14 into m into 2 into V minus V1 by 2 by 1000 into 100 by m 1.4 into m into 2 into V minus V by 2 by m k. Kajal-Hall method is not applicable to compound containing nitrogen in nitro and azo group and nitrogen present in the ring, as nitrogen of this compound does not change to ammonium sulfate under this condition. Halogen carriers method. A known mass of organic compound is heated with fumic nitric acid is in the presence of silver nitrate containing in a hard glass tube known as carrier's tube. In a furnace, carbon and nitrogen present in compound are oxidized to carbon dioxide and water. The halogen present forms the corresponding silver halide. It is filtered, washed, dried and weighed. Let the mass of organic compound taken is equals to mg. Mass of AgX formed is equals to m1g. 1 mole of AgX contain 1 mole of X. Mass of halogen in 1 m1g of AgX is equals to atomic mass of X into m1g by molecular mass of AgX. Percentage of halogen is equals to atomic mass of X into m1g by molecular mass of AgX. Sulfur. A known mass of organic compound is heated in a carrier's tube with sodium peroxide or fuming nitric acid. Sulfur present in the compound is oxidized to sulfuric acid. It is precipitated as barium sulfate by adding of barium chloride solution in water. The precipitated filter was dried and weighed. The percentage of sulfur can be calculated from the mass of barium sulfate. Let the mass of organic compound taken is equals to mg and the mass of barium sulfate formed is equals to m1g. 1 mole of BaSO4 is equals to 233 gram BaSO4, 32 gram sulfur, 1 M1G BaSO4 contains 32 into M1, 233 gram sulfur. Percentage of sulfur 32 into M1 into 100 by 2 to 3 into M. Phosphorus. A known mass of organic compound is heated with fumic nitric acid, whereupon phosphorus present in the compound is oxidized to phosphoric acid. It is precipitated as ammonium phospholipidate NH4 thrice PO dot 12MoO3 by adding ammonia and ammonium molybdate. Alternatively, phosphoric acid may precipitate as MgNH4PO4 by adding magnesium mixture, which ignition yield Mg2P2O7. Let the mass of organic compound taken is equals to Mg and mass of ammonium phospholipidate is equals to M1G. Molar mass of NH4 3PO4 12MoO3 is equals to 1877 gram. Percentage of phosphorus is equals to 31 into M1 into 100 by 1877 into M1. Percentage of phosphorus is estimated as Mg2P2O7. Percentage of phosphorus is equals to 62 into M1 into 100 by 222, where 222 U is the molar mass of Mg2O7 the mass of organic compound taken, M1 the mass of Mg2P2O7 formed, and 62 the mass of 2 phosphorus atom present in compound Mg2O27. Oxygen. The percentage of oxygen in the organic compound is usually found by difference between in total percentage compound and the sum of the percentage of all element. However, oxygen can also be estimated directly as follows. A definite mass of an organic compound is decomposed by heating in terms of nitrogen gas. The mixture of gaseous product containing oxygen is passed over red hot coke. When all the oxygen is converted to carbon monoxide, the mixture is passed through warm iodine pentoxide. When carbon monoxide is oxidized to carbon dioxide, producing iodine, on making the amount of CO produced in equation A equal to amount of CO used in equation B by multiplying the equation A and B by 5 and 2 respectively. We find that each mole of oxygen liberated from the compound will produce 2 mole of carbon dioxide. Thus 88 gram carbon dioxide is obtained if 32 gram oxygen is liberated. Let the mass of organic compound taken be Mg, mass of carbon dioxide produced be M1G. M1G carbon dioxide is obtained from 32 into M1, 88 gram of O2. Percentage of oxygen 32 into M1 into 100 by 88 into M. The percentage of oxygen can be derived from the amount of iodine produced. Also, presently the estimation of element in the organic compound is carried out by using micro quantities of substance and automatic experimental techniques. The elements carbon, hydrogen and nitrogen present in compound are determined by apparatus known as CHN. Elemental analyzer. The analyzer required only a very small amount of the substituent and displays the value on screen within a short time. A detailed discussion of such method is beyond the scope of the book.